You're absolutely
Okay,
right.
we're gonna get started.
Yeah. I don't want to go.
Hello, everyone. Good morning. I'm Samaya Dash from UCSB, and I'll be chairing this session. Thanks for attending. We have a session on uncertainty in geospatial data. We will have 4 presentations, and we have our first speaker here, Evgeny, who is actually my student, and he will be presenting our paper on mapping spatial and temporal variability in mobility patterns in California during 2020 to 2022. Okay, Evgeny, the floor is yours.
Should I be placed somewhere close to the microphone?
Yeah, maybe it was that.
Maybe over there.
Over there. All right. Good morning, everybody. Can you guys hear me? So, thank you for an invitation to present here. My name is Evgeny, and I will be presenting on behalf of 2 of my co-authors, Samaya Dodge and Alex Rudolph. And we are from UCSB. So let me start by saying that the last 2 years have been marked by COVID-19, right? Everybody has gone through that COVID-19. Everybody has done research that was connected or related to COVID-19. We at the Move Lab had that opportunity as well. And we at the Move Lab study movement. So we were interested in how the movement connects to COVID-19. And obviously this connection, this linkages is two-way, right? The mobility influences the spread of the virus, but at the same time, this potential to get the virus, to contract the virus, can curb the mobility. And we have seen different papers spring up in that direction. There was a lot of things on disease modeling. There were some things on non-pharmaceutical interventions and their effectiveness. We as geographers were interested in looking at the spatial and temporal patterns in our data. The flip side of the COVID-19 pandemic was that a lot of the data sources, mobility data sources, became available. So we essentially went from the data poor environment that existed before COVID-19, well, we had some data, but not a lot on aggregate mobility in the United States, to a data-rich environment. And so to some, that's more of a data-driven geography notion. And so there were different companies that started publishing mobility data. Now, we as geographers are interested in how the data is aggregated, and obviously that matters for our research outcomes. And a lot of the data that was published, it originally came from the individual trajectories that were aggregated at some level and reported, say, at the county level for the United States. There are many different issues that show up when you look at aggregation. Obviously, the privacy thresholding algorithms, every company has their own algorithm, and we don't necessarily know how they affect your outcomes, the aggregated outcomes. At the same time, we're not really aware of how that influences the data representativeness. So our main goal, the big picture questions are as follows. How do different types of mobility data influence our research outcomes? In other words, if we use each specific mobility data set, how does that influence the hypotheses that we generated and then accept or reject? And then the other one is, can we use mobility to characterize the pre-COVID, during COVID, and post-COVID mobility and the situation? Can we get at what was going on in terms of how people moved, looking at mobility data sets? And this is just some of the companies that published their data. We looked at 10 different data sources. There were about 26 mobility indicators. And obviously, every company has their own mobility index, and there's no one definition of what mobility is. Mobility is a very fluid concept, right? So whenever you look at different indices, it's just part of what the movement is and the piece of movement that it's trying to capture. So for today's talks, I decided to focus on 2 data sources, the Apple mobility trends and Google mobility trends. So both of those companies publish their data daily at the county level for the entire United States. They've stopped publishing it now, but you have about 2 years worth of data. Now, for Apple, the data came from their navigation app, and that was the number of requests that users that were driving to some direction have requested. And that was in percentage points related to the baseline. The baseline was before COVID-19. Now, for Google, they published 6 different mobility indices based on the categories of the places, like grocery stores, bars, transit, many others. They also published those in percentage points in relation to the baselines. Now, the baseline was different in 2 data sources, but still it wasn't percentage points. we geographers are interested in the temporal and spatial coverage of our data. And what you see here are two representations of that. The color intensity denotes the number of non-Bayesian observations in the data. So first of all, in terms of the temporal coverage, we see a relatively fixed coverage for Apple data. There are some gaps in Google data in September of 2020. That's associated with the changes in the methodology that they've had. A more interesting case is actually a geographic coverage. We see that some of the counties are either missing a lot of values or they don't have values at all. Now that's related to the privacy threshold in the algorithms. And obviously there are some least populated counties in California, like Modoc, Trinity, Plumas, Sierra, and Alpine. And so they just, if there's not enough people residing in a specific area, they just null all the values. So you essentially end up with no values at all. So you can't really make any inferences for those areas based on this data. Coming out of all of that effort and all of the data that was available, we took it as an opportunity to develop the VASA. That's a visual analytics tool that we developed at MoveLab, UCSB. Here's our GitHub repo. I invite you to give it a try. So VASA offered two visual displays that I'm going to use today and as a demonstration and the presentation. It's free and open source, written in Python. So VASA offers two different visual views. The first one is what we call recency consistency map. The other one is called line path scatter plot. Now, since we are talking about mobility, and the VASA looks at spatial autocorrelation, the spatial autocorrelation breaks down your data into two types. There are spatial outliers and spatial clusters. Now, the clusters are separated into two groups, hotspots and cold spots. So when we're talking about mobility and hotspots would denote higher than average mobility in the counties that's located next to other counties with higher than average mobility. For cold spots, it would be the opposite, would be lower than average counties, lower than average mobility counties located next to other lower than average mobility counties. And so looking at this over here, the first thing that we noticed here is the recency. So we mapped the recency. How recent is the cluster? How recent is the hotspot or cold spot? We notice by the color intensity. So the more intense the color, the more recent it is. And you can see that there's a lot of recent hotspots in Hollywood area, in Santa Monica Beach and Venice Beach. This is the census block groups level for LA. Now, the other thing that we've mapped was the consistency, and consistency is just the number of times that specific county or a census block group was classified as a hotspot. So if we had an observation period of 50 weeks and it was classified as a hotspot for 50 weeks, that would be high consistency. That would be a larger marker size, right? You know, over here, we can see that a lot of the census block groups in LA, in downtown LA, were very consistent. So they were classified as hotspots for an extended period of time in the observation period. The one to the right, the visual display to your right, is a non-spatial representation. So it checks the temporal trajectories of individual census block groups here, but you can change the unit, of course, and I will show you at the county level. What you should note here is that the closer those trajectories are to the 45 degrees line, the more consistent they are. So once again, we're mapping the consistency, but the consistency is mapped onto the y-axis. So the closer they are to the 45 degrees angle, the more consistent they are. You can see based on that temporal view, that a lot of the cold spots were not consistent throughout the observation period, and a lot of the hot spots were. And you can sort of see that on the map, right? There's quite a few cold spots in the observation centers. Well, let's go back to our data, the California in 2020 throughout 2022. So when we look at this map, so this is the recency and consistency map. When we look at these two maps, the first thing that we notice is that both data sources were able to capture the cold spots in the Bay Area. And that makes sense since the Bay Area was one of the first ones to implement the stay-at-home order. And also Bay Area had a very high proportion of the IT jobs that are really easy to decrease mobility. You don't have to be in the office to work. So that's very logical, and we see that both data sources can capture it. Now, a more interesting aspect of it is the hotspot behavior. Now, the hotspot is the higher than average mobility. So we can see that Google data was able to capture that better. And all of the hotspots in Google data are very recent and very consistent. So they have been hotspots throughout the observation period, which was the last 2 years. Now, as to the reasons why that is happening, we know that the way the two data companies collect their data is different. Apple is mostly navigation based. whereas Google uses the smartphone's data, not necessarily the requests for navigational directions. So as we know, a lot of the things in Northern California, there's national forests, campsites, wineries, they were closed for some period of time. In 2020, they've reopened in the summer of 2024, but you had to have reservations. So we can still see. But I think that the hotspots in Google are associated with the increased mobility towards the natural areas, people hiking, going on the trips.
You should see it in the Sierra then.
Yes, that's a good, that's a
You
good
should have
comment.
seen it in the Sierra as well, but Northern Cal is different.
Right. And yes, obviously, I would welcome your comments.
We'll talk about that.
Yes, let's talk about it at the end of the presentation. So this is the line path scatter plot. The one thing we notice here, and as I said, we are interested to get some information about COVID-19. So we can look at mobility and maybe get at what was going on with COVID-19. And I've mapped here different variants of the COVID-19. There's Alpha, Delta, Omicron, and Beta. And we can see that Apple data sort of plateaus. The cold spots, they plateau around June 2021. So we could basically assume that it was not able to capture the variation in mobility that were associated with those different variants of COVID-19. Whereas Google data was able to do that, and you can see that on this plot. The other thing that we notice is that the hotspots are, well, that just supports the previous view that we looked at. The hotspots are more consistent. Now, this does not necessarily apply to California only, and to two data sources. As I said earlier, we've looked at 10 different data sets, and this is just another representation of the differences that we see in our data. This is a different mobility indicator called the percentage of sheltered people. So that's the percentage of people sheltered at home. The hotspots would denote higher than average, so more people staying at home. We call it spots, less people staying at home. But so there is obviously a lot of similarities here in, say, like the West Coast, some of the Northeast, but I would like to point your attention to some of the differences. So the first one is the central United States, Iowa, Nebraska. The clusters here are a lot, so they are more recent for cubic data. They are less recent and less consistent for SafeGraph data. The other two important or interesting things that we note here is in Michigan, Wisconsin, and Minnesota. Once again, the recency and consistency is different. Now another aspect of data uncertainty, and this session is about uncertainty in our data, is how representative it is of the larger populations, right? Because whenever you look at mobility indices, it's always a sample. So these four graphs, they try to assess representativeness of the user base from those data sources that there's only four here that we could get the data for. So basically on the y-axis, you have the proportion from the user base of the applications. And on the x-axis, you have a census population. So the closer the center line and the counties that denoted in points. So the closer the points are to the center line, the more closely they align to the actual representative sampling. So we can see that there is a lot of things going on in larger metropolitan areas. So the data for large metropolitan areas such as Los Angeles, Chicago, which is Cook County, the Houston and Harris, Texas, there are some issues. Now, obviously, it matters. So the whole reason behind demonstrating that we can see different picture depending on the data source that we use. I've demonstrated it for Apple and Google in California throughout the last 2 years. I've demonstrated it for Cubic and SafeGraph for the entire United States. And obviously, depending on what data source we're using, we're going to end up with different statistical outcomes or different research outcomes. So we should be aware of that. And a lot of the papers that were published during the COVID-19 pandemic, they either used one data source, they could have used two data sources, but it's really, our statistical outcomes really depend on what data source you used. As you have seen, Apple have missed the hotspot behavior entirely in California, which was demonstrated in the previous slide. Now, another important aspect when it comes to mobility is that there's no one definition of mobility. There's no one perfect metrics that measures mobility. So there are different indices. They are part of a bigger picture. And they obviously tell you just about one aspect of our data. So we as geographers should be aware of that. And with that, I'd like to thank you guys for your attention and open the floor to the questions and thanks. to UNICEF for the funding, and thanks to my co-authors.
Are there any questions?
There's a question over there.
Yes, thank you for your, thanks for this presentation. I think this is very interesting and especially your presentation is very nice and clear. I have one question regarding the differences among these different data sources. Like in those maps you
Yeah,
show,
do you remember which one?
yeah, like this,
Uh-huh.
you observed some differences between the two maps. And I guess that you have also produced a set of maps to compare the different data sources, the results of different data sources. My question is, have you conducted any quantitative measurements regarding in terms of their differences, rather than just like observation?
So like qualitative or quantitative?
Quantitative,
Quantitative.
yes.
So for quantitative, we have not done anything like entirely quantitative to see. It is something that we were wondering about. So obviously, as geographers, we're interested in where the data sources agree the most, where they disagree the most. And so obviously, this is one of the interesting cases. I actually had put this in the appendix. We had two interesting cases in this one is South Dakota. Where we sort of noticed this very interesting. These are qualitative. There's a case studies that are very interesting to like demonstrate what was going on. We see this like great divide with the Mississippi, the east of Mississippi, the west of Mississippi, and South Dakota, and the interesting divide between urban and rural in Georgia. So case-based, but yes, we are definitely thinking about quantitative. Good question, thank you.
Yes.
Yes.
Can you go back to the previous map?
For the online.
All right. This one?
No, the South Dakota example.
Oh,
I'm just trying to figure out. Okay. All right, so that's not the Mississippi River. It's the Missouri River
It's Missouri.
is one thing. So, and also South Dakota, that's just the great population divide, because west of that river is desert. Is what you have.
well, they're different landscapes, right?
They're absolutely different landscapes. The population density decreases by almost 50%
Right.
as you go from the Missouri River to the western boundary. So, and you have a bunch of Native American Indian reservations out there too. So, and their data gets handled differently. So
Yeah, I know.
just want to point that out that
Yeah,
you might want to fix your map.
in color, but we've mapped the counties with Native American majority. And they are, yes, to the west of the river.
Yeah, well, I mean, the Wind River Native Indian Reservation is not on there. So
The what
the
reservation?
Wind River Native Indian Reservation, which is right on the Missouri River. So.
So those are counties with majority, maybe if it's not majority.
It's in South Dakota.
Just Standing Rock, yeah. and
Standing Rock.
Standing Rock
Not Rosebud, sorry.
with their
And
same
then Rosebud is not on there either.
Rosebud, yeah. So, but they defined this as counties with a Native American majority, which.
Yes, that's majority.
Yeah. It's another way of looking at it.
So it's an interesting case study. I just wanted to make sure you fix your map. So the next time you show it to somebody, it's correct.
Yes.
Yeah.
So-
Maybe we can go back to this after
Yeah.
the session.
Yeah.
Yeah, very good. Well, thanks, Evgeny.